Let's take a look at thrust and impulse. This is kind of maybe the third piece in the momentum unit. Impulse is a word we use for the change in momentum. And it's usually when some object is, there's a force being applied over a time period and that object experiences an impulse, meaning a change in its momentum. So impulse, by definition, equals delta P. And there's two versions, right? There's the algebra version and there's the calculus version. The impulse something gets is a force, and since this is a delta T, this really is an average force. So it's then the average force over that time period equals the object's change in momentum. And if you think of the units there, it's in Newton seconds, not newtons per second, Newton seconds. So, an impulse of like 40 Newton seconds, you could apply a 40 Newton force for 1 second, or maybe a 20 Newton force for 2 seconds. So you're still going to change the momentum of the object by 40 Newton seconds, or 40 kilogram meter per seconds, just the unit of momentum. If you have a variable force that's changing over time, well, then you need calculus. This would be an example of a graphical view of calculus where they give you a graph of F versus T. The area under the curve is the impulse. Again, just remember, you also know that force is the rate at which you change momentum. Just think, momentum is mv, force is ma, and the derivative of v is a, thus the derivative of p is f. These are just opposites of each other, right? Force is the rate at which you change your momentum. The accumulation of force over time is then the change in an object's momentum. Remember, it's not the momentum, it's the change in, because the object could have had momentum at the beginning of the scenario. If you think about thrust, all it is doing is rearranging this impulse equation and solving for the force. So if the change in momentum, the impulse, is equal to some force times the time period, what we can say is we can just divide by delta T, and we can say force is, again, it's the same thing as this. It's the algebra version of the derivative. The force is the rate at which we change our momentum. And momentum, we can write in this case as delta M times V. Now, normally we say M delta V, but in a thrust case, this is like, a fire hose, an exhaust of like a jet engine or a helicopter, any of those things. What you're doing is you are throwing things this way, exhaust, and so then the object goes this way with the thrust. If you want to know the thrust this way, all you have to tell me is what are you ejecting, how much mass per second you're ejecting, and then you multiply it by that escape velocity or the exhaust velocity or the exit velocity. Any of those words would be true. And again, this is kind of the thrust equation. The force of the thrust is equal to the number of kilograms per second you're exhausting times the exhaust speed. So if you think like of a space shuttle, right? Your space shuttle, it's exhausting things that way, and it wants to exhaust a whole bunch of stuff per second at a big velocity, and then that will give the lift, or that will make the jet ski go forward. Any of those things, a boat, right? All of these things, you throw something to the right if you want to move to the left, and you want to throw a whole bunch of it really fast. So the thrust equation, the impulse equation really are just talking about the change of momentum. The units here are just kind of fun because it's kilograms per second and then an exit velocity. So if you had like, we're going to do a water hose here in a second. Okay, so just quick examples of both thrust and impulse. So if I apply 40 newtons of force to 2 kilograms for 4 seconds, find the final velocity of the object if the original velocity is 5. Well, thinking about it in this case, what is delta P? Well, delta P is going to be that force, 10 newtons, for 4 seconds. So I get a change in momentum in 40. And you think about, well, what's the original momentum? Well, the final momentum should just be the original momentum. Oh, I said final, but I wrote delta. I said the final momentum is the original momentum plus that change in momentum. The final momentum is just the mass times the final velocity. The original momentum, well, it's a 2 kilogram object moving at 5 plus the impulse of 40. So this is 2 VF equals 10 plus 40 is 50, and I get a final velocity of 25 meters per second. So they can play around with velocities, kilograms, seconds, newtons, all that stuff. And if you wanted to go old school, you could. You could even just use F equals ma and figure out the acceleration of that force on that mass. This is just F equals ma if you want to go old school. Old school would have been easier on this one. Take a 10 Newton force to a 2 kilogram mass, and you get an acceleration of 5 meters per second squared. Accelerating for 5 meters per second for 4 seconds increases your velocity by 20, and if you were going 5 to begin with, you now are going 25. Again, momentum and forces are just two different sides of the same coin. One's, one's the calculus version of integrals, and one's looking at derivatives. Okay, so that's that first one. Here is kind of a graph. We know that the area under the curve is going to be the impulse, or the object's change in momentum. If this peak force, meaning right there, is 20 newtons, then the area, again, area is just a triangle, so it's 1/2 base times height, and the impulse there is 40 Newton seconds as well. And if I had a mass and I had no velocity, then what is the velocity of this thing? Well, in this case, the change in momentum is just the momentum of this thing, because the first momentum is just 0. So 40 equals 5 times what? And you get a velocity of 8. All right, so I went from 0 to 8. Cool, so it's a graphical view, kind of an algebra view. And then this one's kind of looking at thrust. So it says a water hose is like sitting up here, and it is throwing out water. It's like exactly 1/2 of a kilogram per second is leaving the end at a speed of 10 meters per second squared. And then what is the thrust? And again, we know that the thrust force is going to equal that delta m over delta t. And if you wanted to do the calculus version of it, it would be dm dt. It's the rate of change of the mass per second, and then at that exit velocity. So it's really just going to be that 1/2 kilogram per second times that 10 meters per second is going to give you a 5 Newton force. Okay, so the next part says if there was a hose attached to a 2 kilogram box. So if the hose was attached to here, well, what would happen? Well, the thrust would cause that mass to accelerate. And so 5 newtons would make 2 kilograms accelerate the other direction at 2.5 meters per second squared. Okay, so the algebra is not too bad on thrust. Again, one of the biggest things is that you realize that impulse is just the change in momentum of something. You change something's momentum by applying an external force over a time period, or you can accumulate it with calculus if the force is changing. A graphical point of view is just looking at the area under the curve. Thrust is just rearranging, and this should make sense that the thrust, again, it's just a force, that the force, the reactionary force this way is equal to how many kilograms per second you're launching that way times how fast you're launching it. So if you're a space shuttle, or you're a jet ski, or you're a fan boat, you chuck stuff this way and you go this way, right? Just take rollerblades and throw a heavy ball one way, you go the other way. Just pretend, you're constantly throwing a heavy ball. You'd be constantly then accelerating the other direction. Okay, hopefully this gets you introduced to thrust and impulse and allows you to get started on the bookwork.